Hello, welcome back. In this segment, I'm going to show to you how the RSA blinding mode works. This mode is necessary to prevent timing attacks. In the past, we have seen how RSA works. So I will quickly summarize the formula, the model, and show to you how we can introduce so-called blinding inside of the existing model. Okay. So the approach works as follows. First of all, very quickly, how does RSA work? The core of the RSA is this function, which takes some ciphertext. Well, the first encryption function takes some plain text M, rise it to power E mod n. E and n are public keys. Okay, and this produces ciphertext C. So you can imagine M power E divided by n. The remainder is C. That C is the ciphertext. How is the decryption working? The decryption works by taking the ciphertext C, rise it to the private exponent D, mod n also. And this we have discussed earlier that if E and D are properly chosen, you get an M back. Okay. What I mean by properly chosen is that E times D is one mod of either Euler's torsion function or lambda function. Okay, we talked about a couple of alternatives. Okay, anyway, one mod, I will use Euler's torsion function here. Some implementation uses Carmichael function that we talked about in the previous segment. Okay, so one mod pi of n, some function pi of n. Okay, pi of n is the Euler's torsion function, supposed to be pi. Okay, all right. So this is the classical model. The problem is that if you directly code this D, which is the private D, only the owner of the public private key pairs would know that. If we code it as it is, it turned out that one can perform timing attacks. Like since D is on the exponent, right? The based on timing profile, like a power profile or timing profile, the attacker was able to extract lots of bits of the private exponent D. Okay, so the idea is to make it difficult for the attacker to extract the private exponent D. How can we do that? So the inventor of RSA, one of the inventors, came up with this idea that instead of directly doing C power D mod n, first generate random R, right? In the group Z star n, which we talked about. That means the n is relatively primed to both P and Q. No prime factors whatsoever common between R and n, right? Remember, n is itself is a composite number made of two primes, distinct primes P and Q. Okay. Random number R is chosen first from Z star n, which means R inverse exists. That's the idea. Okay. So what is that we are going to do? We are going to take the incoming ciphertext C as part of the decryption. First, we raise R to E, okay, and multiply it with the ciphertext C, okay, all in mod n. Okay, so we are doing R power E times C, and then we apply the decryption exponent D on top of it in mod n, okay, which is nothing but R power ED. R power ED is nothing but 1. So remember, ED is 1 mod pi of n. Therefore, ED will cancel out and you get an R. And you will be having the regular C power D in mod n. Okay. So we learned earlier that C power D mod n will give us M. That's something we already proved earlier. So what we get back here is R times M. So all you have to do now is you need to get rid of R. So we multiply it by R inverse. Okay. R inverse exists because R is relatively prime to n. That's the reason R has been picked from Z and star, the group Z star n. So R and R inverse will go away. So you get M. Okay, this is basically the idea of the blinding mode. Some implementations, the blinding mode is turned on by default. So you, as a programmer, you don't have to even worry about it. There are some implementations where you have to configure it because, as you can see, there's a performance overhead. You need to generate a random R first, and then you need to compute R power E second, and then you need to compute R inverse third. So 3 extra steps you're doing to make it difficult for an attacker to find the value of D based on timing data. Now, the timing data is not corresponding to just C power D. It corresponds to R power E, and then it also corresponds to R inverse. So multiple things are mixed, so making it difficult for an attacker to find the value of D. I'm not saying it's impossible, but this is the fix proposed by one of the inventors of RSA. Okay, so to summarize, all we are doing is, before doing the regular decryption, we generate a random number R. We compute R power E first, and then apply the R power E times C power D, which means the regular decryption. And E and D will cancel out because E times D is 1 mod pi Fn. So what you're left with is C power D mod n, which is nothing but M, because we already proved that. So R and R inverse will cancel out if you multiply it with R inverse, and therefore we get M back. Okay, so this is basically the idea of blinding mode, which I will show to you in a quick demo now. Okay, so the demo goes as follows. What I'm going to do is just take a simple implementation, right? Just to get this idea across. I have implemented the RSA decryption using blinding as follows. You're given a ciphertext and the private exponent D and the public exponent N and E, public modulus N and exponent E. First step, I generate a random group element, and then I compute the R inverse in mod N. And then I compute, as I explained on the whiteboard, R power E mod N. And then multiply it with the ciphertext C. And then I take the R inverse to cancel out the R. That's all. So this is basically the blinding that will make it difficult for an attacker to predict the value of D. Okay. In the previous segments, I was showing you the decryption was like this, C power D mod N. As you can see, I'm still using it, but I changed the content of C, right? I modified the content of C by introducing some randomness. So the base value C is different. Furthermore, R inverse is also part of the computation. Therefore, the attacker has challenges now because of 3 different things that he doesn't know exactly. Okay, he doesn't know D, he doesn't know C because I modified the C. He doesn't know the R inverse. So all these 3 things make it difficult. Okay, all right. So let's check that this is correct. So first is the standard key generation. I'm using 1024 for demo purpose. Usually you should be using 2048 or more. Encrypt a random message, and then I'm calling the encryption function. By the way, I'm not using padding. I'm just showing the raw RSA function, which is perfectly fine for this demo. Okay. In practice, you most often wanted to use padding before you call the encryption. So as you can see here, I am doing the blinding and check whether am I getting the message back. Okay, let's run it. Okay, assertion passed. Let's make mistakes so that we can check whether, yep. So that's good. Okay, so all we did is basically modify the decryption function a little bit. All we're doing here is generate a random element and multiply R power E, and then cancel out the R at the end by multiplying it with R power with R inverse, which exists because R is a random group element from Z star N. Okay, that's all. That's basically the idea of RSA blinding. Okay. Very quickly, the random group element is basically looking for a random element until the GCD is 1 with N, which is very likely in the first attempt because there are, in large N, most of the elements have no prime factors common with N. So that's the reason why this is very quick. All right, that's all. Thank you.